At the end of video 11, and here's a screenshot of where we left off in video 11, we asked what might be involved in figuring out exactly on which dates there were 10 hours of daylight in the day. And we saw that that could be expressed as a mathematical equation where we took our formula, which predicted the number of daylight hours, and we said, when will the daylight hours be equal to 10? Now, solving this for t, determining the values of t from this equation, is not something that we were able to do just yet, because the value of t is inside of the sine function. So the question becomes, how do we get the value of t out from inside a sine function so that we can solve equations like this one, where our equation has a sine function with a variable inside of it. Today is going to be the first day talking about how exactly that is done. Today we're going to introduce a function called the inverse sine function, whose purpose is to destroy sine and to liberate variables like t from within sine. So by the end of today, we should be able to figure out the domain and range for the inverse sine and inverse cosine functions. We should be able to figure out what is an appropriate input or output for these inverse sine and inverse cosine functions, and we should be able to evaluate these functions at a certain location. Tomorrow we're going to talk about inverse tangent, and then the day after that we're going to talk about how to use these inverses to solve equations containing sine and cosine and tangent. To begin with, let's briefly review the concept of inverses. The inverse of a function, let's say the function's name is f of x, was some other function whose purpose in life was to destroy the work of the function f of x. The inverse undoes the work of f of x. And the purpose of inverses was to help us to solve equations. For an example, in Pre-Calculus 1, you learned that the logarithm was the inverse of the exponential function. So suppose that we wanted to take an equation where we had an input value inside of the logarithm, and we wanted to solve this equation. We wanted to get t out from inside the logarithm. To destroy the natural logarithm, we deployed the inverse function exponential. That way, the exponential and the logarithm annihilate each other, and we have successfully freed t from inside of natural log. That allows us to be able to solve for t. Now, in order for a function to even have this arch nemesis, to even have a true inverse, there was a condition that needed to be satisfied. The graph of the function f of x needed to pass what was called the horizontal line test. And that required the graph of f of x to satisfy the property that no matter what horizontal line you drew, any horizontal line will cross the graph in at most one location. And the beauty of functions that had a true inverse, the beauty of functions which passed the horizontal line test, well, there are two beautiful things about that situation. The first thing is that if you're trying to solve an equation where you have f of x equals some number, for example, you have natural log of something equals 4, then you know right away that that equation is only ever going to have one solution. For example, the equation in the example above had the single solution t is equal to this one number. And not only that, that singular solution can be found using really only the inverse. In the previous example, if we wanted to get t out from inside the natural log, the only tool that we needed to use besides some basic arithmetic was the inverse, the exponential function. One tool to find one solution. But that's a property that's pretty special to functions that actually pass the horizontal line test and have true inverses. Let's look at a function that would not have a true inverse. For example, f of x equals x squared. In this case, if I drew a horizontal line, such a line passes through the graph in more than one location. So f of x fails the horizontal line test. As a result, this function does not have a true inverse. Which means that equations that contain square, for example, if I had 3x plus 1 squared equals 16, this might have more than one solution. So in order to find all of the solutions, some tricks and extra special techniques are required. To solve this particular equation, for example, you probably used two tools. The first tool that you used was the square root. The square root does help you to undo square. So this might be called maybe a fake inverse or like a pseudo inverse. We know that the square function doesn't have a real inverse, but there is still a tool out there that helps us to get rid of the square function, and that tool is called the square root. However, because the square root is not a real inverse, an extra tool is used, that extra tool being the plus minus. If I use the square root, I can get rid of the square on 3x plus 1, but in order to get all the solutions, I need to use an additional tool, plus minus, and that is as a result of the fact that the square function doesn't have a real inverse. Alright, having concluded that review from Pre-Calculus 1, let's see what consequences that discussion has when we're talking about the trigonometric functions. Just like the square function f of x equals x squared, the sine and cosine functions are not going to have a true inverse. They're going to fail the horizontal line test in a rather extreme fashion. Any horizontal line that you draw is going to cross the graphs in infinitely many locations. 2 locations per bump, basically. So neither sine nor cosine has a true inverse. They fail the horizontal line test when you graph them. However, just like we did for f of x equals x squared, it's possible for us to come up with what I call a pseudo-inverse for the trig functions. Just like with the square root function, we're going to use the pseudo-inverse to get one of these solutions to sine of input equals some number, or cosine of input equals some number. And then we're going to use an additional tool, just like plus minus, to get all the other solutions to these equations. And spoiler alert, the additional tool that we're going to use, that tool is going to be the unit circle. So the name that we give the function that plays the role of the pseudo-inverse of sine is arcsine, also known as sine with a -1 above the sin. And it's defined by the following rule. The input of arcsine is a y-coordinate on the unit circle. That is the meaning of the input of the inverse sine function. And the output is the angle between -pi/2 radians and pi/2 radians, at which sine outputs that y-coordinate. So let's get some practice evaluating arcsine, evaluating the quote-unquote inverse sine function at various values. Someone asks me, what is the value of arcsine of 1? So the first thing that I'm going to note is that in this problem, 1 represents the y-coordinate on the unit circle. That's the data that's being given to us when they put an input of 1 into the arcsine function. And what we want, the angle, specifically the angle between -90 degrees and +90 degrees, where sine outputs this 1. Now, let's have a quick look at the unit circle. The location where the y-coordinate on the unit circle equals 1 is located right up here, at the very tip top of the unit circle. So which angle is going to position us there? Well, there are several different angles that will position us at the North Pole on this unit circle. For example, an angle of pi/2 radians. But there are other angles which position us at this same location. -3 pi/2, for example, or 5 pi/2, etc. However, we're going to ignore all these other coterminal angles, and our answer is going to be the single angle which lives between -90 degrees and +90 degrees. That the value of arcsine with 1 plugged into arcsine is the angle pi/2. So that's how arcsine is defined, and arccosine is defined in a very similar manner. Arccosine is the name for the pseudo-inverse of cosine. For this function, arccosine, the rule is that the input represents the x-coordinate on the unit circle and the output is asking for the angle specifically between 0 and pi radians, where not sine but cosine outputs that x-coordinate. Someone asks me to evaluate arccosine with 1 plugged in. So in this problem, the input of 1 represents the x-coordinate on the unit circle. And what is this problem asking for? It's asking for the angle, specifically the angle between 0 and pi radians, where cosine outputs 1. So as usual, to answer this question, I'm going to look to the unit circle, draw a quick sketch, and I'm going to identify a location on this picture where the x-coordinate is equal to positive 1. There's only one coordinate with that property, which is on the far right side of the picture. Now there are several different angles at which this x-coordinate is attained. The first one being 0 radians, for example. But also, technically, any other coterminal angle would put us at the same location. However, arc cosine is designed to produce the specific angle that lives between 0 and pi radians. So as a result of that, I'm going to reject all these other possible answers because they're not in the right range. In answer to this question, I would say that arc cosine of 1 is equal to 0 radians. Let's evaluate arc cosine at 1/2. So we want angle specifically between 0 and pi radians where cosine outputs this given 1/2. So let's go back to that unit circle reference image that we introduced in video 4. Now looking at this reference image, there are actually two different locations on the unit circle that have an x-coordinate of positive 1/2. The first one is located up here, x equals 1/2, and the second one is located down here in quadrant 4, x equals 1/2. So based on the definition of arc cosine, what do you think my final answer should be? Should I answer with the angle pi over 3, or should I answer with the angle 5 pi over 3? Remember, always try and remember that arc cosine is always looking for an angle between 0 and pi radians, which means an answer like 5 pi over 3 is not permitted. Yeah, cosine does output 1/2 at that location, but the angle is of the wrong size. We want an angle between 0 and pi radians, so the angle that achieves that condition is pi divided by 3. Let's try it again. Someone asks me to evaluate arc cosine with -1 over 2 plugged into this function. So here I am looking at the unit circle again, in search of locations where the x-coordinate on the unit circle is -1/2. And there are two such locations. One of them up here in quadrant number 2, corresponding to an angle 2 pi over 3. The other one down here in quadrant number 3, corresponding to the angle 4 pi over 3. Now, which one of these angles am I going to choose for my final answer? I'm going to choose 2 pi over 3 because it's in the right range. Suppose that someone asked me to evaluate arcsine with pi plugged in. Arcsine is a function which is designed to give us an angle. For arcsine, the angle has to be between -pi over 2 and pi over 2, at which sine outputs in this case, outputs the value of pi, which is being plugged into arcsine. So here's the issue though. Sine cannot ever output pi, because sine is outputting values on the unit circle, and the unit circle has a radius of 1, the outputs of sine are limited and are trapped between -1 at their smallest and +1 at their highest. So if we ask sine to output a value like pi, this is simply too big. Sine cannot output a value that is this large. So arcsine of pi is not a number. This is just undefined. We cannot find the angle at which sine outputs pi because pi is too big for sine. Similarly, if someone asked me for arc cosine of 2, cosine can't output a number as big as 2. It's larger than 1 in magnitude, so it's too big. And therefore arc cos of 2 is also undefined. So as a note, the domain of arc cosine and arc sine is from -1 to +1. These are the only values that can be plugged into those two functions, because these functions are the inverses of sine and cosine, and sine and cosine have a range of -1 to 1. So just like there are some values that cannot reasonably be plugged into arcsine or arc cosine, there are also some values that we reasonably cannot expect to be produced by arc cosine or arcsine. For example, someone says, okay, hey, I know that sine at the angle 3 pi over 2 is equal to -1. If I plug in an angle 3 pi over 2, sine outputs -1. So if someone asks me for the value of arcsine with -1 plugged in, our input and output always just swapped. Is the output of arcsine equal to the angle 3 pi over 2? The answer is no. This statement is false. And the issue is that arcsine of -1 is specifically designed to produce the angle between -90 degrees and 90 degrees, at which sine outputs -1. Now, although 3 pi over 2 is certainly an angle where sine outputs -1, the size of the angle is not a match to the range of the outputs of inverse sine. 3 pi over 2 is too big, it's larger than pi over 2. Instead, if I wanted to determine the value of arcsine of -1, I would need to find an angle between -90 and +90 where sine outputs -1. So the answer to that question, arcsine's value, would be equal to -90 degrees itself, not +3 pi over 2. That concludes today's material. We began by reviewing the topic of true inverses of a function and pseudo-inverses of a function. We found out that sine and cosine don't have true inverses because their graphs fail the horizontal line test. But it's still possible to define a pseudo-inverse to sine and cosine. These functions give us one angle at which cosine/sine output a specified given value. and therefore they can be used to find one solution to a problem like sine of something equals number. By using arc cosine and arc sine together with the unit circle, we can find all the solutions to trig equations, which is what we'll do a few videos from now. Now, just a quick note, I have been pretty careful to do my best to refer to arcsine and arccosine as pseudo-inverses of sine and cosine, because we know that these functions don't really have inverses. But it's not common for other people to be this careful with their terminology, and so you may and probably will see arccos and arcsine called simply the inverses of cos and sine, even though cos and sine technically don't have inverses. This is just for convenience, I would say. Calling them pseudo-inverses can get a little bit annoying after a certain amount of time, so arccos and arcsine are usually just called inverses for convenience sake, even though there's a little bit of inaccuracy in that language.